Hello everybody, this is Professor Jing. In this week's lecture, we will discuss Anova. Here are the learning objectives. As a result of this class, you will be able to first describe analysis of the variance, which is Anova, and then explain the rationale of Anova, and then compare the experimental design, and lastly, test the equality of two or more means. Specifically, we're going to talk about completely randomized design, randomized block design, as well as the factorial design. Analysis of variance allowed us to compare means of more than two groups. It is a method of analysis we use in research design with a continuous variable and one or more categorical independent variables. The simplest type of analysis of variance is one-way analysis variance with just one independent variable that distinguishes three or more groups. In analysis of variance, independent variables are often referred to as factors. The factors are categorical variables that represent groups, often experimental or quasi-experimental conditions, also referred to as the level of a factor. People can also refer to group or level as the cell in a factorial design. Um, in one-way analysis of variance, there are just one factor with three or more levels. Suppose we have to compare the health of three groups of females that consume different diet. For example, normal, strict vegetarian, and lacto-vegetarian. An epidemiologist rates their health on the scale from 0 to 10. You might think of this to perform three pairwise t-tests, compare two groups means at a time. This is not a good idea because the family-wise error rate will be inflated. The error rate is the probability of falsely rejecting the null hypothesis or falsely concluding there is a significant effect when the null is in fact true. So if it performs one test, the error rate is equivalent to the significant level, which we determine ourselves and normally set at 5%. When we perform more than one test, the family-wise error we refer to the probability of at least one of those tests, resulting in a false rejection of the null hypothesis. This probability is approximately equal to the number of tests times the significant level. If we use analysis of variance, we don't have to worry about the inflated error rate. Analysis of variance allow us to decide whether the group are samples from the same population distribution with one and the same mean, or whether they're from different population distribution with different means. It does so by comparing the variance of response variables between the groups with the variance within the groups. This diagram is based on the number of exploratory variables and the nature of relationship between x and y. We will discuss ANOVA in these three types of experimental design: completely randomized block, and factorial designs. Okay, let us talk about the use of ANOVA in completely randomized design. Completely randomized design is very popular in medicine and public health. Research subjects are randomized assigned to treatment. Those subjects should come from the same target population and have similar characteristics. We assume that they are homogeneous. They are one independent variable or one factor, and within this factor, there are two or more level or groups. For example, receiving standard health education versus personalized health education. In this example, we can perform one-way ANOVA to see the mean of two groups are the same. Please note that there is one continuous dependent variable and one categorical independent variable in the ANOVA model. What we're testing is the equality of two or more population mean. For example, if the mean score of a test are different between the two groups. In the next few slides, we will discuss the overall F-test in one-way analysis of variance. We will look at the assumption, the statistical null and alternative hypothesis. We will see how to calculate the test statistic, determine the p-value, and how to interpret the results. Suppose we want to compare of three groups of female that consume different diet: normal, strict vegetarian, and lacto-vegetarian. An epidemiologist rates their health on scale from 0 to 10. First, we need to know and check the assumption of analysis of variance. These are equivalent to the assumption of multiple linear regression, although they might look a little different. First of all, the observations should be independent of each other. Random selection or random assignment in experiments should take care of this. If the observations are dependent by design, for instance, with repeated measure of the same participants or paired participants, you should use repeated measure in the analysis of variance. In our example, we will assume females were randomly assigned to the conditions. Secondly, the response variable should be normally distributed in each group. Let's create a histogram in SPSS. Let's say the histogram looks fine. Even if they didn't, moderate violation of normality isn't problematic as long as the sample size are large enough. Let's say at least 10 observations in each group. If the sample size are small and very skewed, you should use a non-parametric test instead. Thirdly, analysis of variance assumed homogeneity of variance, which means the population variance is assumed to be the same for all groups. Moderate violation of homogeneity variance is not problematic if the group size are equal. If the group size are unequal, a rule of thumb is that you can still perform analysis of variance as long as the largest standard deviation is no more than twice the size of the smallest standard deviation. The null hypothesis states that all population means are equal. The alternative hypothesis states that at least one population mean differ from the rest. This specifies that there is a difference somewhere. It doesn't specify for which groups we expect the difference or in what direction. Therefore, we cannot say that the group 1 is not equal to the mean of group 2, not equal to the mean of group 3. Here are some visuals that help you to see the different situations. Your null hypothesis is the mean that are the same. For the alternative hypothesis, not all means are equal. It is possible that mu1 and mu2 are the same, but they are different from mu3. Or it's possible that mu1 and mu3 are the same, but they are different from mu2. You can see that argument is at least one mean is different from the others. By now, you should have some ideas about one-way ANOVA. ANOVA compares two types of variation to test equality of means. If the treatment of variation is significantly greater than random variation, then the mean are not equal. Variation measures are obtained by partitioning total variation. The total variation you observe can be split into two parts. Variation due to treatment, which is called sum of square treatment, which reflects the variation existing among groups due to treatment. Variation due to random sampling reflects individual difference within groups, which is called the sum of square error. The calculation of total variation is the same as calculation of variance for a set of observations. You need to have the mean of the independent variable regardless group. Then you calculate the difference between each observation and the means, square each difference, and then add up to have the total. For SST, you will need to calculate the mean of each group, then calculate the difference between the mean of each group and the grand mean. Square the difference, multiply by the sample size of each group, and add those up to have the treatment variation. For SSE, you will use the mean of each group, then calculate the difference between individual observation of each group and the corresponding group mean. Square the difference, add all together to have SSE. The test statistic F equals the between group variance divided by the within group variance. One thing to look out for is the difference in presentation between statistical software packages. The between group mean sum square is often denoted using the name of the factor. The within group mean sum square is often refers to as the mean square error, abbreviated by MSE. In the previous lecture, we have already calculated the two degrees of freedom associated with F distribution. They are the numerator between degree of freedom, the number of group minus 1, and the denominator within or the error degree of freedom, the total number of observations minus the number of groups. Here is a table that summarizes what we have discussed so far for one-way ANOVA. Be aware of that n equal to the sum of sample sizes of all population. Also, please note that all values are positive. Think about why. And because they are square terms, the degree of freedom and sum of square are additive. Mean square is not. The test statistic follow an F distribution with two separate degrees of freedom. Let's say in our example regarding dietary effect on health, we find an F of 3.793 with 2 and 46 degrees of freedom. Since the F test is non-directional, we always look into the right tail of the distribution. With the significant level set at 0.05 using the table, we find the critical F value with 2 and 40 degrees of freedom is 3.2317. The observed F value exceeds this value, so we know that the p-value is smaller than 0.05. SPSS software provides an exact p-value of 0.03. We can reject the null hypothesis and conclude that at least one of the diet group differ from the others in terms of mean health rating. Let's look at an example to exercise our knowledge on ANOVA. Pause here to read the example and think about whether we should use ANOVA to answer the question. Work on this example by yourself. Move on to the next slide to see the solution. Suppose the assumptions are met. The null is the mean are the same. The alternative is they are not the same. So the test statistic is 25.6. Look at the table. We find for alpha equal to 0.05. Degree of freedom are 2 and 12. The corresponding F value is 3.89. Since the observed F is 25.6, we know P must be less than 0.05. Therefore, we reject the null hypothesis. We can conclude that there are evidence that the population mean of weight loss are different. If you use SPSS, you will see an output like this. Additionally, p-value will be reported so that you can make the statistical decision. If you request box plot for 3 groups in SPSS, you will see an output like this. It is obvious that the population means are different. When the analysis of variance leads to a rejection of the null hypothesis of no difference among population mean, the question naturally arises regarding just which pairs of means are different. In fact, the desire is to carry out a significance test on each and every pair of treatment means. We can use LSD, the least significant difference method, without adjustment of type 1 error if other comparisons were planned in advance. Otherwise, we can use Bufferoni method in which type 1 error need to be adjusted. We use Fisher's least significant difference method, which refers to the use of the residual standard deviation, the square root of within group variation instead of the pooled standard variation to calculate the standard error. So in each pairwise comparison, we estimate the standard error based on the variance in all groups. Here is the formula. If the assumption of homogeneity is violated, you should use the formula that makes no assumption about the population variance. Since we'll be making multiple comparisons, we should correct for use the inflated family-wise error rate. The probability that at least one of the comparisons will result in a false rejection of the null hypothesis. There are many correction methods, are often referred to as the multiple comparison method. We will consider 2 of those. The Bufferoni method and the Tukey honestly significant different method. Bufferoni method provides a pairwise comparison of the mean. To determine which means are significantly different, we must compare all pairs. For example, you have 3 groups, then there are 3 pairs you need to test. mu1 equal to mu2, mu1 equal to mu3, and mu2 equal to mu3. If you have 4 groups, then you have 6 pairs to test. The Bufferoni method involves dividing the desired overall alpha by the number of comparisons and using the resulting corrected alpha for the individual comparisons. With this correction, the actual probability of falsely rejected the null hypothesis will be smaller than or equal to the desired overall alpha. In many cases, the correction is overly conservative, resulting in a smaller alpha or less power. To start, we must select a value for alpha, the confidence level. We will select alpha equal to 0.05. In Bufferoni method, the idea is to divide this family-wise error rate among the k tests. So each test is done at the alpha divided by k level. Therefore, divide this family-wise error rate among the k tests, where k is possible pairs. Then you get the mean of each group and MSE. Apply those numbers with the sample size of 2 population to the formula. You will get the t-value. Tukey's honestly significant difference method is less conservative. The actual probability of falsely rejecting the null hypothesis is closer to desired overall alpha. It results in more powerful tests and narrower confidence interval method than the Bavarani method. Tukey's method uses a test statistic distribution slightly different from the t-distribution, so we will leave the calculation of the test statistics, confidence interval, and the p-value to software. Let's look at another type of study design, randomized block design. The randomized complete block design was developed about 1925 by R. A. Fisher, who was seeking the method of improving agricultural field experiment. The randomized complete block design is a design in which the unit to which the treatment are applied are subdivided into homogeneous groups called blocks, so that the number of experimental units in the block is equal to the number of treatment being studied. The treatment are then assigned at the random to the experimental unit within each block. So it should be emphasized that each treatment appear in every block and each block receive every treatment. Some important characteristics of a randomized block design that you should know. In a randomized block design, research subjects are assigned randomly within blocks, and the blocks are assumed homogeneous. There are an independent variable which has 2 or more levels, and there is one blocking factor. Are the mean training times the same for 4 different methods A, B, C, and D? These can be medication for cancer. You can see that the treatment are randomly assigned within each block. Blocking factor could be age groups. Like when we Anova, we test the equality of 2 or more population means. Unlike Anova, you have a blocking variable to deal with, which is typically a nominal variable. Randomized block F-test needs to meet the same assumption, normal distribution, equal variance, and no interaction between treatment and the blocks. Probability distribution of each block treatment combination is normal, and probability distribution of all block treatment combinations have equal variance. The block and treatment effects are additive. This assumption may be interpreted to mean that there is no interaction between treatment and blocks. In other words, a particular block treatment combination does not produce an effect that is greater or less than the sum of their individual effects. The consequences of a violation of this assumption are misleading results. One need not become concerned with the violation of the additivity assumption unless the large mean is more than 50% greater than the smallest. Again, your alternative hypothesis is at least one population mean is different. Be careful with your statement for the alternative. It can be shown that the total sum of square for the randomized complete block design can be partitioned into three components, one each attributable to blocks SSB, treatment SST, and arrow SSE. The total variation needs to take into account the variation due to the blocking factor. The formula for calculating F ratio is shown here. We saw MST and MSE in the previous slide. MST refers to the mean square for the treatment, and the MSE is the mean square for error. The appropriate degrees of freedom are p minus 1 and n minus p minus b plus 1, where p is number of treatment, b is number of blocks, and n is total sample size. F-test is always one tail. If the calculated F value is greater than the critical value, then you reject the null hypothesis. Here is an example of randomized block design. Carefully read the description and work on this question. Move on to the next slide for the solution. Please note that the critical F value with alpha equal to 0.05, degree of freedom equal to 3, and 12 is the 3.49. Since the calculated F larger than the critical F value, we know P must be less than 0.05. Therefore, we rejected the null and conclude that there is evidence that the population mean are different. Another common experimental design is factorial experiments. In the experimental design that we have considered up to this point, we have been interested in the effect of only one variable, the treatments. Frequently, however, we may be interested in studying simultaneously the effect of two or more variables. We refer to the variables in which we are interested as factors. The experiment in which two or more factors are investigated simultaneously is called a factorial experiment. The different designated categories of factors are called level. Suppose, for example, that we're studying the effect on the reaction time of 3 doses of some drug. The drug factor then is said to occur at 3 levels. Suppose the second factor of interest in the study is age, and it is though that 2 age groups under 65 years old and 65 and older should be included. We then have 2 levels of age factors. In general, we say that factor A occurs at A levels and factor B occurs at B levels. In a factorial experiment, we may study not only the effect of individual factors, but also, if the experiment is properly conducted, the interactions between factors. When we have a factorial design, we should use 2 ways Anova. Factorial design are time efficient. It can also save you effort as you will be able to examine 2 factors of interest at the same time. As I mentioned earlier, it allows you to explore interactions and controls for confounding variables. In the factorial experiment, all the observation may be used to study the effect of each of the factors under investigation. The alternative, when 2 factors are being investigated, will be conducted 2 different experiments, one to study each of the 2 factors. If this were done, some of the observation will yield information only one of the factors, and the remainder will yield information only on the other factors. To achieve the level of accuracy of the factorial experiment, more experimental units will be needed if the factors were studied through two experiments. Generally speaking, the assumption of two-way ANOVA are normally distribution, equal variance, and independence of errors. These are the same as in one-way analysis of variance, the observation should be independent. In cases with random assignments, it takes care of its assumptions. If the observations are dependent by design involving repeated measures or paired observations, we should use repeated measure analysis of variance, which is not the focus of this course. Second, the response variable should be normally distributed in each. The histogram can be used to virtually check the normality. Analysis of variance is robust against moderate violation of normality. If the sample are large enough with at least 10 observations in each group, so we don't have to consider using the non-parametric test. Third, the analysis of variance. The variance need to be homogeneous or the same. In cases with unequal sample size, the largest variance should be no more than twice size of the smallest variance, so you will proceed. This is an example of a two-way ANOVA table. You have I levels of factor A and J levels of factor B and K observations. We specified statistical hypotheses for each of the main and interaction effects. For each main effect, the null hypothesis states that the relevant marginal population means are equal. The alternative hypothesis states that at least one population mean differ from the rest. The interaction effect specifies that the difference between the mean on one factor are the same for each level of the other factor. For example, the difference is in population mean. Health for vegetarian and normal food are expected to be the same for female receiving hormone therapy compared to the females not receiving hormone therapy. It helps to know that the total sum of square, all the variation in the response variable is equal to the sum of square for treatment A plus the sum of square for treatment B plus the sum of square for interaction plus within group or arrow sum of the square due to random sampling. Here is a two-way ANOVA summary table. It has source of variation df, sum of square, mean square, and f. The output of two-way ANOVA test in SPSS is organized in the same way. Although we talked about interaction in epidemiology previously, it is helpful to quickly review the concept. Interaction occurs when effects of one factor vary according to the levels of the other factors. When your intersection is found to be statistically significant, you will need to report it, and the interaction can be complicated. Before diving into the output of SPSS or any calculation, will be detect potential significant interaction using a data table and a graph. In data table, if the pattern of cell means in one row different from another row, it is a sign of interaction. In a graph of cell means, if lines cross, then it is a sign of interaction. Here is a sample that can help you to better understand interaction. The bottom graph shows the effect of gender and dietary groups on systolic blood pressure. When interaction occurs, the line cross, you can see that the relationship between average response and dietary groups differ between the males and females. When there is no interaction, the lines do not cross. Basically, the relationship between X and Y is the same regardless of gender.